So maybe your teacher did a lesson 10 today, maybe they did a different lesson today, but regardless, it is review. It's review from last semester. We calculated average rate of change. So when you hear the phrase average rate of change, what should your mind automatically go to? And I will have it up here for reference, but this is something you need to memorize if you don't already. You had to memorize it in Unit 3 and Unit 4, and I told you average rate of change is something that they ask for everything. So for each different type of function that we talk about, they're going to ask you for the average rate of change. What have we called this in the past? What does it help us find? What does it help us find for linear functions? Slope, which is average rate of change, but slope specifically for linear functions, we usually don't care where you look at on the table or on the graph because slope for linear functions is the same no matter where you're looking because linear functions are your straight line. My average rate of change will be the same whether for those I'm looking from like here to here or from here to there. So pay attention. Linear functions have the same rate of change throughout. Do exponential functions have the same rate of change throughout? Are exponential functions perfectly straight line? So then the answer is no. That's why when we started talking about average rate of change, we made sure that in the problem it specified where you need to look. So usually it'll say like from where X is 4 to where X is 6. So maybe that's like year 4 to year 6 or something like that. You would then have to, if it's a table, find those X values. If it's a graph, still you need to find those X values. What else? If it's an equation that you have to plug in X and solve for the Y, then you need to do that. But in order for this equation to work, or this formula rather, you need two coordinates. So whether that's in table form, whether that's in function notation, whether it's on a graph, you need to identify your x1, y1, your x2, y2, plug it into this and solve. Okay, so exponential functions, depending on where you look, so they usually look like that or like this. If I'm just looking at a really small interval of time, then maybe I don't expect that average rate of change to be big at all. But if I'm looking over like a large period of time, then I should expect it to be pretty big because exponential functions either increase or decrease at really fast rates. It just depends on where you're. If they ever have you interpreting your average rate of change, whatever label is on your Y's, so like from the notes, it was number of stores. Put that over whatever label is on your X. So like X in our notes today was years. So if my average rate of change is 22, then on average, they open 22 stores for every 1 year. Right? So all of this we've done before, even for exponential functions, you just might not have realized they were exponential. So be able to score 80% or higher on the lesson 10. I'll go make sure that everyone has that. But otherwise, if you so far don't have 80% on all your practices thus far, do this one first and then go back and try to get 80% on the others. Some of you I'll be pulling to take the quiz you missed Friday, so be aware of that. Any questions? We're on number 2, lesson 10. A study was conducted to analyze the effects on deer population in a particular area. F will be an exponential function for the population of deer t years after the study began. And it says if f of t equals a times b of t, sorry, I didn't mean to freeze this, and the population is increasing, select all statements that must be true. So b in our exponential functions, b is what? Your common factor. So if my common factor is greater, that goes with growth or decay. Like this one saying that it's greater than 1, so would that be for growth or decay? If I'm multiplying by number 10, what should happen? And you could try that out. You could do any number times like 1.01 and it will increase. So that if it's greater than 1, it's growing. If it's less than 1, then it's doing what? Decaying, good, or decreasing. And in this situation, it says that the population is increasing. So which one should I automatically exclude? Okay, good. Don't pick this one. It said the population's increasing, not decaying, not decreasing. Then it says the average rate of change from year 0 to year 5, table 7, from year 0 to year 5 is less than the average rate of change from year 10 to year 15. You don't have the numbers to do the math and compare. However, if you are looking at an exponential function that is growing, it probably looks something like that. Let's say that here is where year 5 is. And then we could do year 10 right there. And year 15, I can't even see on my graph. Let's just say that. Would you expect the average rate of change to get bigger or smaller as we continue on the graph? Bigger, because we know that when you're multiplying, and the more you have to multiply that big number by that same amount, the rate of change is increasing way more than it did if you're just looking like from here to here. So if I look at like my notes for today, this is where that kind of comes into play. Because there's no like turning point, I guess, it's either constantly increasing or constantly decreasing. It'll get steeper the more you go to the right versus like at the beginning where it's less. So you'd say, I would say that this is true then. The average rate of change should be less here than compared to year 10 to 15. And then this one contradicts the one I just selected. We would not expect the average rate of change to be greater toward the beginning of the graph. Maybe if we were talking about something that was decaying, sure, but not something that's growing, we'd expect it to grow more toward the end. And then lastly, A is greater than 0. So what is A in our exponential functions? A stands for. So does that make sense? Does our initial amount have to be greater than 0? Yeah, because we're talking about deer. In order for our deer to increase, I have to have deer to start with, right? So this would have to be greater than 0 in order for it to make sense in the problem. And you have to pick those exact 3 in order for it to count. Yours might be shuffled, so don't just blindly pick. Make sure you look at it at the details. But questions on this one? Questions on any others? Serenity? Question 5. So this was from Friday, so hopefully you got 80% or higher, or if not, then we can probably ask right now. So the graph shows an exponential relationship between X and Y. Complete the following, we need to create an equation representing the relationship. Solve for Y when X is -1 and solve for Y when X is -2. So let's see. Notice that it has the part with the exponent in there already. And it looks like they're using this type of setup that we've seen before. All right, so we already know what the B is, like I don't need to fill in anything for that. What I need to identify is my A, my initial amount. So based on what we've talked about, what's gonna be my A? Based on this graph. 50 is correct. All right, it's not the first dot you see from left to right. It's whatever your y-intercept is always your A. It's whenever time is 0. So that means A is going to be 50. So I need you to type in a 50 there for this part. I'm going to put my answers like this, so that way I don't have to scroll so much and it looks all weird. But A just has to be 50 like that. I don't know why I put that. All right, for B, when it says what's the value of Y when X is -1, well, I do see -1 on my graph, but I can't really, like, you could try to estimate it, but estimating is not usually like a good strategy. So what you should do then is you know the equation now. It's 50 times 2 to the t power or to the x. So if we're trying to solve for when X is -1, your safest bet would be to just put that in the calculator. Of course, you can kind of see the pattern as I'm working backwards. It's decreasing by, like it's halving each time. However, this is still your safest bet. You would type this in your calculator and it should be 25. If not, tell me, because then that just means you're using your calculator. For part C, what is the value of Y when X is -2? Well, if I know that this is 25 and we're halving each time going backwards, for this one, it should be half of 25, which is for that one, you would type this in your calculator. And that would be your safest bet, but it is 12.5, or at least check the key. Yeah. All right, any other questions from any practice? Anyone from Friday? Cameron? Number 4 on today. Okay, so the function f gives the number of copies of the pestle which weeks after it was published. Gives you an equation. Select all domains for which the average rate of change could be a good measure for the number of books sold. When we talk about domains, we're talking about all the what in a function? All the x's. And in this case, they're giving that as weeks. So when we're saying from like 0 to 2, let's see this. And maybe 10. You could also type in this equation in Desmos, graph it, and take a look if you like. But it says, for which domains would the average rate of change be a good measure for the number of books sold? That was a weird one. You won't have something like this on your test, I will say that. But as far as your homework, I would say that the bigger gaps in time are the ones that are more toward the middle. would probably be a better indicator, is what I'm gonna go with. So I think 0 to 2 will be too small. We'll show the answers here in a second. I think that one will be too small and not a good representation for the number of books sold, because you'd only expect like a little bit. So I'd say that's too small. I'd say 5 to 7, again, I'm also thinking is too small of a range, although it is more toward the middle, so we kind of like it. Let's see, I think it's gonna be here. 5 through 10. I don't like this one. I might just delete it. Let's see what it says. Okay, so it does like those two. The ones that I did not like that I said were too small. But it likes those for some reason. I might just delete this question. You won't be asked that on your real test. So it's kind of a weird. Maybe what it actually means is that, okay, I kind of see what it's saying. Let me go back to the notes real quick. So you know how we were calculating the average rate of change between a lot of these numbers? And we said that like it was 139.5 on average. Are you guys listening? Okay. So when we said, for example, that it's 139.5 on average, that's really not what's happening every year, right? So like the bigger time frame you're looking at, the less it kind of looks like it's changing by that much, even though that is the average rate of change. The smaller time frame that you're looking at, like from 1987 to 1990, the more it looks like it is increasing by 22, for example. So that's why with questions like that, it does want the small ones. But again, like you don't really worry about your test surface. So questions on any other problems? Wade? On lesson 10? Okay, a moth population is modeled by this equation. And we want what was the moth population when it was first measured. So if this is my equation and it looks like my setup that we're used to for exponential functions, which letter of this will give me my initial amount? So it would be whatever is in the A position. In this one, it's 500,000. I would not put commas unless it specifically says to, because normally in a calculator, you wouldn't want to put a comma. So I think it will still accept it if you did put a comma, but just don't unless it tells you. What was the moth population after 1 week? Well, it did express the exponents as weeks. After just 1 week, you should expect, based on my B value, to multiply it by half. Or you could also just do the math, plug it in, put a 1 there, and it should give you the correct answer. What's 500,000 times 1/2? So that's what this one should be. But again, like the safest bet would probably, like instead of me doing it that way, would probably be just to do this and put the exponent as however many weeks. But it should be 250,000. What about 1.5 weeks? Rounded to the nearest thousand, like not TH, 1,000. So let me put that in my calculator. So for that one, I do 1.5 as the exponent. All right, and it said 1,000, not thousandth with a TH. So where I think it wants us to round to is here. Wherever you are rounding, look to the right So here's my thousands place, not thousandth with a TH, thousand. Based on the number to the right being a 7, does that 6 stay a 6 or does it go up 1? It goes up 1. And then these will now become zeros. So 177,000 would be you rounding correctly. And then use technology to graph the population and find out when it falls below 10,000, rounded to the nearest tenth. So I'm going to graph my original. What I will do is instead of a W, I'm going to put an X though, because I don't know if it'll allow me to do a W. All right, so I put an X for the exponent. I can't see anything, but what I do want to see is when the Y falls below 10,000, so I'm gonna adjust my window for that. I'm gonna make my Y-axis go maybe a little bit above 10,000. Maybe I'll zoom out. All right, so I'm clicking and dragging on my line. It looks like, let's see if I can zoom in. Okay, let me see if I can zoom in further. Because it wants you rounding to the nearest tenth. So let's see. 5.6 it looks like. That's as close as I can get. Let's see if that's the answer. And yep, that's it. So for that last one, for graphing technology, you just type it in, use X's though instead of the W. I adjusted the window so that I could see near the 10,000 a bit better. And then I just clicked and dragged until I got close. And rounding to the nearest tenth would be 1 decimal spot. So that's about 5.6 consistently. Okay. Any other questions, depending on how fast it is? We might have time for one more. Going once. Going twice. All right, we'll make sure, like, if it needs to